Section 5.5, Integer Exponents, the Quotient Rule, and Scientific Notation. In an earlier section, we developed a pattern with exponents that helped explain what happened when we got 3 to the 0 power. So what we saw was 3 to the third was 27, 3 squared was 9, 3 to the first was 3, and 3 to the 0 was 1. And we said that that was reasonable because as each time the exponent decreased by 1, we were dividing by 3 to get to the next step. And so if we continued that pattern, we got to the point where 3 to the 0 was equal to 1. Well, let's suppose the pattern continues. And let's divide by 3 again. Well, 1 divided by 3 is 1/3. 3 to the negative first power is the same as 1/3. Continuing on. 1/3 divided by 3. 1/3 divided by 3 is the same as 1/3 multiplied by 1/3, which is 1/9. And 3 to the negative third, as you might guess, is 1/27. So notice that, for example, 3 to the third and 3 to the negative third are reciprocals. Similarly, 3 to the second and 3 to the negative second are reciprocals. So the negative exponent tells us to use a reciprocal. For any non-zero real number a to the negative nth power is the same as 1 over a to the nth power. That is to say, a to the negative nth power is the reciprocal of a to the nth power. So, for example, if we had 2 to the negative third power, that is the same as the reciprocal of 2 to the third power. 2 to the third power is 8, so we would have 1/8. 2 to the negative third power is equivalent to 1/8. Why don't you try the next two on your own? Nine to the negative first is the same as the reciprocal of 9 to the first. 9 to the first power is simply 9. Y to the negative fifth power is the same as the reciprocal of y to the fifth power. Nothing can be simplified here. Now here we have 4 to the negative first times 4 to the negative second. Using one of our rules from a previous section, the product rule, we can write this as 4 to the negative 1 plus negative 2. And that would be 4 to the negative third power. Using what we've now learned about rules for about negative exponents, we can write this as the reciprocal of 4 to the third power. 4 to the third power is 64, and so we would write 1 over 64. In these exercises, we are asked to simplify the expression, writing the answer using positive exponents. So in the end, we have to make sure that we have no negative exponents present. All right, so if we had x to the third times x to the negative ninth, applying our product rule for exponents, we could write this as x to the 3 plus negative 9. So that would be x to the negative sixth. However, we are asked to write the answer using positive exponents. X to the negative sixth is the same as the reciprocal of x to the sixth. And so we would write 1 over x to the sixth, and this is simplified. R s to the fourth to the negative third power, using our rules for exponents, would be r to the negative third power, s to the fourth to the negative third power. Let's leave the r to the third alone for a moment. S to the fourth to the negative third can be written as s to the 4 times negative 3, using our power to a power rule from a previous section. So we now have r to the negative third, s to the negative 12th. However, we don't want negative exponents, so r to the negative third is the same as the reciprocal of r to the third. S to the negative 12th is the same as the reciprocal of s to the 12th. Multiplying the fractions, we would have 1 over r cubed s to the 12th. Let me show an alternative method for the same exercise. We could have removed the negative exponent right at the beginning. We have a quantity to the negative third power. That would be the same as the reciprocal of the quantity to the positive third power. Now, using our rules for exponents, we would have 1 over r to the third, s to the fourth to the third. And using the same principles as in the other example, we'd have 1 over r cubed s to the 12th. Either approach it works. So use what works best for you. I'd like for you to pause and try the next exercise on your own. I'm going to apply the product rule right away. And so I would have a to the negative second to the negative fifth times b to the negative fifth. So that would give me a to the negative 2 times negative 5 times b to the negative 5. And so that would be a to the positive 10th power, b to the negative 5th power. And so that would give me a to the 10th times the reciprocal of b to the 5th, or a to the 10th over b to the 5th. Thinking of that a to the 10th as an a to the 10th over 1, multiplying fractions. Now, if you just went with this in the other method, we could have written this as 1 over a to the negative second b to the 5th, which would give you 1 over a to the negative second to the 5th, b to the 5th. And so you'd have 1 over a to the negative 10th, b to the 5th. Now, here's where it gets a little bit tricky. But what you notice is, we went through the first time, we went through it in blue, and we had the a to the 10th in the numerator. And notice that we have this a to the negative 10th in the denominator. So basically, if you have something with a negative exponent, if you have a factor with a negative exponent, you can put it in the other part of the fraction with a positive exponent. So what I'm going to do is I'm going to take this factor, this a to the negative 10th, I'm going to bring it up front. I'm going to bring it up top with a positive exponent. And so we would have a to the 10th power still over b to the 5th. All right, let's build a pattern and see what happens. What if we had x to the 6th power divided by x to the 2nd? Well, recalling what exponents mean, this would simply mean it would be x times x times x times x, x times x. There are 6 factors of x in the numerator. The denominator would be x times x. And what I see is there are 2 factors of x in common between the numerator and denominator. Removing them, I would have x to the 4th over 1, which is more simply x to the 4th. Now that looks interesting because 6 subtract 2 is 4. Well, wait a second, what about this one? If we did that, we'd have 3 subtract 8 is negative 5. Will that work here? So let's see. The numerator would be x times x times x. The denominator, 1, 2, 3, 4, 5, 6, 7, 8 factors of x. Removing common factors. And remembering there's a 1 in the numerator, we would have 1 over x to the 5th, which, recall, is equivalent to x to the negative 5th. So what we see here is, if we're dividing numbers with the same base, we can keep the base and subtract the exponents. And this is called the quotient rule for exponents. For any non-zero real number a and natural numbers m and n, a to the m divided by a to the n is equivalent to a to the m minus n. And like I said before, basically what this says is to divide numbers with the same base, keep the base, subtract the exponents. So I'd like for you to pause and try these 3 exercises on your own. Y to the 9th divided by y to the 4th would be y to the 9 minus 4, which is y to the 5th power. Z to the 2nd divided by z to the 10th would be z to the 2 minus 8, which would be I was getting ahead of myself there. Z to the 2 minus 10, which would be z to the negative 8th power. Now, in general, we won't like to leave our answers with negative exponents, so we will write this as the reciprocal of z to the 8th. B to the negative 3rd divided by b to the negative 9th. Be careful with the signs here. Would be b to the negative 3 subtract negative 9, which is b to the negative 3 plus 9, which is b to the 6th. So now we have a few that are a little bit more complicated. Let's say we had z to the 8th divided by z to the... I'm sorry, those aren't z's, those are 2's. Not that it really matters. 2 to the 8th divided by 2 to the 3rd would be 2 to the 8 minus 3 power, which is 2 to the 5th. Now, 2 to the 5th is 32, so we can just write that as 32. 1 over y to the negative 4th. Now, I'm going to go about this the long way this time. We would have 1 over. Now, y to the negative 4th is itself the reciprocal of y to the 4th. So now we have 1 divided by 1 over y to the 4th. So I'm going to write it like that. 1 divided by 1 over y to the 4th. Division is multiplication by the reciprocal. And so we would have y to the 4th. So earlier I said basically one of the tricks is if we have something with if we have a factor with a negative exponent, we can bring it to the other part of the fraction with a positive exponent. And so this just sort of is an example that explains why that happens. Remembering that negative exponents mean use of a reciprocal, and when you divide, you're multiplying by the reciprocal of the reciprocal. So we would have y to the fourth in the numerator. All right, let's say we had 12a to the sixth b to the second over 8a b to the third. Since this is all multiplications, I can sort of pull the similar things together in their own fractions. So I'll write this as 12 over 8 times a to the sixth over a times b to the second over b to the third. Now 12 over 8, let's see, that's 3 times 4 over 2 times 4. So there's some common factors I can remove. Times a to the 6 minus 1, using the quotient rule, and b to the 2 minus 3, again using the quotient rule. So I'd have 3 halves times a to the fifth times b to the negative first. And so that would give me 3 halves. And let me think of that a to the fifth as an a to the fifth over 1, and that b to the negative first as a reciprocal of b to the first. Multiplying these back out, I would have 3a to the fifth over 2b. All right, why don't you try this next one on your own? Simplify the expression 20x to the negative third y to the second over 45x to the second y to the sixth. Using a similar idea as the previous exercise, let me sort of break it up as 20 over 45, x to the negative third over x to the second, and y to the second over y to the sixth. 20 over 45, I'm going to write as 4 times 5 over 9 times 5. X to the negative third over x to the second is x to the negative 3 minus 2. And we'd have y to the 2 minus 6. Removing the common factors, I would have 4/9. X to the negative 3 minus 2, that would be x to the negative fifth. And 2 minus 6, I'd have y to the negative fourth. So that would give me 4/9 times 1 over x to the fifth times 1 over y to the fourth. Or more simply, 4 over 9x to the fifth y to the fourth. All right, now we're given the expression 3/5 to the negative first power. Well, remember, I've been saying all along that negative says reciprocal. So 3/5 to the negative first power is the same as the reciprocal of 3/5. Well, wait a second. The reciprocal of 3/5 is 5/3. The reciprocal of 3/5 to the first power, which is simply 5/3. So 3/5 to the negative first power is the same as 5/3, the reciprocal. Well, so what if we had 5u over 3v to the negative second power? Using the same exact process, same exact idea, I could write this as the reciprocal of 5u over 3v. Well, the reciprocal of 5u over 3v is 3v over 5u. So I'd have the reciprocal to the second power. Using several of our rules, quotient to a power, product to a power, and simplifying, I'd have 9v squared over 25u squared. All right, scientific notation. Scientific notation is a concise way of writing large and small numbers. A real number A is in scientific notation when it is written in the form b times 10 to the nth power, where b is between 1 and 10, 1 inclusive, and n is an integer. So we have these absolute values on here because basically what we're saying is whether it's positive or negative, it has to be between 1 and 10. The value of the number must be between 1 and 10. All right. So we're asked to convert from scientific to standard notation. We're given the number 3.2 times 10 to the 5th power. Now, I don't know what you remember about raising 10 to a power, but 10 to the 5th power is a 1 with 5 zeros after it. Now, if you remember something about decimals, if you multiply a decimal number by a power of 10, you simply move the decimal point to the right as many places as there are zeros. So since there are 5 zeros here, I move the decimal point to the right 5 places. So that would be 1 place, and then I have to bring in zeros. 2, 3, 4, 5 places. So the decimal moved from here 1, 2, 3, 4, 5 places. And so 320,000. Similarly, 4.72 times 10 to the 7th, well, I'm going to let you try this one on your own. That would be a good time to pause. Write this number in standard notation. All right, 10 to the 7th is a 10 with 7 zeros after it, and multiplying by 10 to the 7th power would equivalently mean move the decimal place 7 places to the right. So 7, 2, there's 2 places, 3, 4, 5, 6, 7. All right, and if we throw in some commas to make this easier to read, we'd have 47,200,000. So if we have a positive exponent on the 10, to get to standard notation, we'd have to move the decimal point to the right as many places. Now what if we had 9.4 times 10 to the negative 5th? Well, remembering our rules for exponents, that would be 9.4 times the reciprocal of 10 to the 5th. And so that would be the same as 9.4 divided by 10 to the 5th. And remember, 10 to the 5th is a 1 with 5 zeros after it. Now, when you divide a decimal number by a power of 10, you move the decimal point to the left as many places as there are zeros. So the decimal point was here. It's between the 9 and the 4. I have to move it to the left. So there's 1 place, 2, 3, 4, 5, and there's my decimal. So 0.000094. Why don't you try the other one on your own? All right, without going through the whole process again, Basically, I'm going to move the decimal 7 places to the left. So, I have the 213. The decimal point was here. I'm going to move it to the left 7 places. So there's 1, and I'm going to need to bring in 6 zeros. Let's just check. 1, 2, 3, 4, 5, 6, 7 places. So, 0.000000213. Alright, so now let's take this in the other direction. Let's start with standard notation and go to scientific. Alright, so remember, to get it in scientific notation, it must be in the form b times 10 to the nth power, where b must be between 1 and 10. So basically, the first thing I'm going to do is find a decimal number in this number that's between 1 and 10. Well, 1.4 is between 1 and 10. So that's my b. Now I've got to decide how many places did I move the decimal. Well, the decimal was at the end of this whole number, and I moved it 1, 2, 3, 4, 5, 6 places. So I have 1.4 times 10. Now I've got to decide, is it a 6 or is it a negative 6? Well, here's the way I like to think of it. Is this a large number, the original number, is it a large number or a small number? 1,400,000 is a large number. Large numbers positive exponent on 10. So 1.4 times 10 to the 6th power. Why don't you try the other one on your own? All right, so we have, what, 3,250,000,000. Again, my first step is to find a number between 1 and 10 out of this. Well, right there, 3.25. How many places did I move the decimal? Well, from the end, 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And this is certainly a large number. 3,250,000,000 is a large number. So this is the same as 3.25 times 10 to the 9th power. All right, a couple more examples. We want to again go from standard to scientific notation. So here I have 0.000001203. Well, right there's my decimal number, 1.203. All right, there's my number between 1 and 10. Now, how many places did it move? Did the decimal move? 1, 2, 3, 4, 5, 6 places. So, I have 1.203 times 10 to the... Now, is this a large number? The original number was not large, it was a small number. And I tend to think small numbers get negative exponents on 10. So I'd have 1.203 times 10 to the negative 6th power. All right, why don't you try the other one on your own? The number between 1 and 10 that's present here is 5.61. To get to there, I'd have to move the decimal 1, 2, 3, 4 places, and this is a small number, so I would have 5.61 times 10 to the negative fourth power. All right, we'll finish off the section with an application. The moon is about 240,000 miles from Earth. Write this number in scientific notation. All right, well, that's not too difficult. 240,000, the decimal number would be 2.4, and I'd have to move the decimal 5 places. So A would be 2.4 times 10 to the 5th power. And again, that would be in miles. If a rocket traveled at 4 times 10 to the 4th miles per hour, how long would it take for it to reach the moon? All right, well, if we recall that distance is equal to rate times time, distance is 2.4 times 10 to the 5th. The rate is 4 times 10 to the 4th. And we wish to know the time. So let's divide through both sides by 4 times 10 to the 4th. See, now here's where scientific notation is nice. So the time would be 2.4 times 10 to the 5th over 4 times 10 to the 4th. Now, if we sort of separate this into two pieces, 2.4 divided by 4 is easy. It's 0.6. 10 to the 5th divided by 10 to the 4th is also easy, because that would be 10 to the 5 minus 4, which is 10 to the 1st. So we'd have 0.6 times 10 to the 1st. So moving the decimal one place to the right, 6. And the units on that would be hours. So scientific notation is nice because it allows us to multiply and divide large and small numbers very easily.